Let's look at a simple example to illustrate some of these points we've been making. I call this the knotty problem. We're trying to come up with an analysis model for an application that will count the number of nodes in a tree structure. And the tree structure is provided as input to this program. The output is just a number. We're allowed to destroy the tree while we do this counting because we're dealing with a copy of the tree. But the problem is all data types must be implemented as classes. There are no pre-existing data types in this application to be assumed. Let's review what we mean by a tree, first of all. A tree is a collection of nodes. Right? That's a node. That's a node. That's an edge. Okay? A tree is a collection of nodes connected by edges or directed links, directed lines. Arrows, right? And a tree is a collection of nodes in which all the nodes have only one parent. So each node in this tree has one parent, except for the root. If you'll notice, the root doesn't have any parents, but all the other nodes in the tree each one has exactly one parent. So something that would not be a legal tree, if I put a node down here and said it had those two parents, that would not be a tree. That would not be a valid tree because this node right here has more than one parent. All right, so let me get rid of those pieces. But this is a tree. Let's see, this is a tree. This is a tree. Oh, this is not a tree. Let me show you something here. This is not a tree. That so far is a tree, but then if we have that, no longer a tree. Right? So that's not a tree. This is not a tree. Okay. How about this? Well, it depends on our definition of tree. So if we say that the definition of a tree is a collection of nodes and edges, directed edges, where each node has exactly one parent except for the root that doesn't have any parents, then this I think would fit our definition because it is a node. There are no edges, but it's one node, so it's a collection of nodes and edges. The collection of edges just happens to be empty. And each node has one parent, except that node right there is the root. So that would be a valid tree. That would be a tree as far as our definition is concerned. Okay? So now let me talk about something else. The study of trees is a branch of something called graph theory. And a tree is a kind of a graph. It's now there are all sorts of graphs. The tree is a kind of graph where the edges are directed links and there are no cycles. Okay. Well, actually, that's a lattice. A lattice is a structure where it's a graph with directed edges, but there are no cycles. A tree is a kind of lattice in which each node only has one parent. Now, there's a subset of trees. There's a special kind of tree where each node has exactly two subtrees. This is referred to as a binary tree. Okay. So this is a binary tree, but this is just a regular tree, but it's not a binary tree because this node only has one subtree. Okay. Now, in the graph theory of trees, there is a theorem. It goes like this. If I start with a valid tree, by our definition, and we remove one of the links, and it doesn't really matter which one the edges, we'll remove one of the edges. It doesn't matter which one we remove, but if we remove it, say we take that one out, let's try that and see. Take that edge out, and what do you get? Two trees. Let's put it back in. Let's take another edge. Let's take this one out. What do we have? Two trees. And it doesn't matter which edge we remove. You can take any one of those edges out, and starting with a valid tree, remove an edge anywhere, you get two trees. This is a theorem that we could prove with mathematical induction. We're not going to take the time to do that now, but it certainly could be provable that way. All right, so now we know what a tree is, And we have this theorem that says you can split a tree by removing one of its edges. You split it into two valid trees. Okay. Well, I came up with an algorithm for counting the nodes in a tree. And here it is. First of all, we're going to maintain a node counter, which initially is 0. And then we're going to get the original tree from wherever it is outside the system and put this tree onto a pile of trees. The pile is initially empty. Okay? So the pile being initially empty, we take this tree from outside and put it on the pile. Now the pile has one tree in it at this point, okay, down here in the algorithm. So now, as long as the pile is not empty, we're going to repeat this logic over and over again. All right, the logic is this. First of all, we get a tree from the pile, randomly select it from the pile. The pile is not ordered or anything like that. We just randomly select one of the trees from the pile. And of course, the first time through this, there's only one tree in the pile. So we get a tree from the pile. We look at the tree, and if it has subtrees, then we'll split it into two trees using the theorem that we just talked about. And we put each of the resulting trees onto the pile. Now, if the tree that we removed from the pile does not have any subtrees, then what is it? Well, it must be a node. Right? And therefore, we found a node. So we'll discard that node, that tree, and we'll increment the node counter by 1. Keep doing this as long as the pile is not empty. When the pile is finally empty, we'll display the current value of the counter on the standard output device. Now, two questions might come to mind here. One, will the pile ever become empty? If we start with a finite tree, we'll have to assume that, finite number of nodes and edges in this tree, can we argue that eventually this algorithm will terminate? Well, in order to do that, both sides of this if statement have to cause the predicate of the loop, the pile not being empty, to tend towards becoming false. In other words, both the then part, splitting the tree into two trees and putting each resulting tree under the pile, and the else part, discarding the tree and putting something back in the pile, both parts have to cause this loop to tend towards terminating. Well, certainly if we execute the second part, the else part, that will cause the pile to become shallower because we remove a tree from the pile and don't put anything back on. So the question is, does the first part here, does the then part of this if then else, cause the predicate of the loop to tend towards becoming false? All right, so we're splitting the tree into two trees. Well, in doing so, each of those two resulting trees is smaller than the original tree. And specifically, it's smaller by one edge. Eventually, if we do that then part enough times, we're going to run out of trees that have subtrees. And therefore, we're going to be forced to execute the else part. And it doesn't really matter what order we do, pull the trees out of the pile. It doesn't matter what order we do the then parts and the else parts. There will be a finite number of iterations through this loop. So I think we can argue that the algorithm will terminate. The second question that might come up is, well, is the algorithm correct? Will the value of the counter at the end of the program, in other words, when the pile is empty, will the value of the counter equal the number of nodes in the original tree? Well, in order to sort of argue that, it depends on a couple of things. One, the way we count the nodes is by incrementing a node counter by 1 each time we find a node. All right? Well, that relies on the fact that the node counter must start at 0. Well, it does. Right up here, we initialize the counter to 0, and then we increment it by 1 each time through the loop. Each time we find a node, we increment the node counter by 1. So that has the effect of counting the nodes. That's no problem there. Is it possible to double count any nodes? In other words, we count a node once by incrementing the node counter, and then somehow we manage to find that node again and count it again. No, that's not a problem because we discard the node at the same time that we count the node. So the only other question remaining is it ever possible for us to miss any of the nodes? In other words, somehow they leak out of the pile and we never get to count them. And no, that's not possible either, because every time we remove a tree, we split it, we still have the same number of nodes. It's just that they're in 2 trees instead of 1, and we put both of those resulting trees onto the pile. And so it's not possible for us to skip any of the nodes either. So I think we could argue that way, then, that the algorithm will correctly count the number of nodes in the original tree. Well, the problem with this is, where are the objects? Okay, where are the classes of objects? We can look at this, and we ought to be able to use the arguments that we talked about earlier about what to look for when you're trying to find the objects. Now, this is an extremely simple example, so it should be easy for us to find the objects, the classes of objects. Okay, we want to diagram each of the classes using the UML notation, right, where the name of the class is in the top of the box. The middle part of the box has the names of the attributes or some description of the data inside the object, and the bottom third of the box has the names. And ultimately, particularly when we get to design, we'll put the whole signatures of all the operations in the bottom. Right now, for analysis, it's just sufficient to name the attributes and name the operations. Okay. So here are room for 3 classes. If we need more, we'll add more boxes. Okay. So we look at our algorithm and see, are there anything in here that would meet our criteria for being a class? Now, what did we say, or object? What did we say about objects? Objects are holders of information. They encapsulate information. They encapsulate the behavior of operations. And furthermore, the operations that the objects have should support an abstraction. So are there abstractions in here? Are there pieces of information that are encapsulated in this description of this algorithm? Well, a lot of times people will say, well, node, right? That's a class. Well, node here, what information does the node encapsulate? Usually when you use a tree structure in a program, the nodes hold information, and that's why you use a tree. And you send messages to the nodes to have the node do things with the information that's encapsulated inside that node. For this tree, the nodes don't hold any information. They're just things that we want to count. So node doesn't fit our definition of an analysis level class because it doesn't hold any information that we care about. It's just something that we want to count. Right? So what else is in here? Well, I don't know. Is edge in here? I don't even know if it is. But it's not a class either because it's nothing we need to remember information about. Well, where do we put the information about the structure of the tree? In other words, the structure of the nodes and the edges. Well, that could go into a class that we can call tree. Okay? So that's really a class. And what is the information inside a tree object? Well, if we remember our definition of tree, it's a collection of nodes. There it is, collection of nodes and directed edges where each node has only one parent except for the root, which has none, no parents. Okay? So that would be the definition of the information encapsulated inside an object instance of class tree. All right, well, let's finish up this tree, the definition of a tree class, by looking at what maybe the operations are. Certainly, there's one operation that's obvious. It's the one that most people come up with first, and that's the fact that we have to be able to split a tree. Right? Where is it? Right here, split. All right, so we need to be able to split a tree. So that's one of the operations on a tree, is to split it. Okay. What else is there? Well, if we look here, what else can we do with trees? Well, here we have get a tree from the pile. But is that an operation on trees? Is that an operation on a tree? It looks like more of an operation on like a pile or something like that. So getting a tree from the pile is not an operation on trees, and neither is putting a tree onto the pile. But what else could we do to a tree? Well, there's one. Discard the tree. Right? So let's add discard to this list. Is there anything else? Well, the other one, the other operation that is on trees, a message that you need to send, be able to send to a tree to have it tell you something or do something. In this case, the operation tells you something about the tree. And it's kind of hard to find here because it's not an obvious, it's not a verb like these other active verbs here, like split and discard. It's there's a verb, it's the verb to be, right? And it's the verb has here, has. So what is the operation? Well, we need to send a message to the tree to ask if whether it has any subtrees. Okay? So has subtrees might be a good name for this operation. All right. Now most classes, well I guess all classes, need to have some sort of an initialization operation. Usually this is in the constructor, but for our purposes, let's just add an initialization here. That's now in our case it was get the original tree. So get initial tree. Okay, so those are some operations on tree. We might find some more, but let's stick with those for right now. Are there any other classes? Well, yeah, I think we sort of found one before. The things about that hold the trees, right? Get it that we can get the tree and we can put the tree in. Okay, that's your pile. So we can create a class called pile. So now, what is the information inside the pile, a pile object, an object instance of class pile? Well, it's a collection of trees, I guess, right? Now let's look at the algorithm and see if we can find some of the operations on pile. Well, I think we found some before. All right, we had get a tree from the pile. Right, let's call that get. By the way, you should use the same names that are in the domain. So in the problem domain, if we call it get a tree from the pile, then the operation on the pile class should be called get. All right, what else? Oh, then we have put, right? Put the tree onto the pile. So there's put. What else is there? Anything else that we can do to a pile? Well, yes, there is. There's another one of the is verbs. And in this case, it is not empty. Or let's simplify that to say it is empty is the operation. Okay, so we want to be able to send the message to the pile and say, are you empty? Okay? Because that will be the guard on or the predicate on our loop. Now, is there any initialization for the pile? Yep. Where is it here? Initially empty. So we'll be able to initialize the pile to empty. There may be other operations. I don't know. Let's hold off on that. Let's see if we can find any other classes in here. You see anything else in here that holds information, encapsulates information, and provides operations on that information? Yeah, well, obviously it's this node counter. Okay, or just counter. Let's just call it counter because we can make a reusable class. Right now we're counting nodes, but in the future we might want to count other things, and so this same counter class ought to be able to be reused whenever we need to count stuff. All right. So what is the data inside or the information inside a counter? Well, it's we can think of it as an integer, but actually it's an integer greater than or equal to 0. We could actually be much more precise about it that way. Right? And now let's see if we can find some of the operations on the counter. Messages that you send to object instances of class counter. Yeah, let's see here. It looks like we need to be able to increment the counter by 1. Okay, increment. Let's just call that increment. What else? Well, it's down here. It's display the counter. Display. And now there's an increment. Is there a decrement? Don't see a decrement in here. Now we may want to put a decrement operation in some cases because this could be a reusable class, and then in some cases you might want to be able to decrement. For our purposes, we don't need a decrement. I'm not going to put it in. The only other operation is an initialize, and it's not really a verb, but it's close enough here. The node counter is initially 0, so we need to be able to initialize the node counter to 0. Now, the classes that we have here is this complete set of classes. Well, let's look at it. One technique that has been effective in small examples like this is what is called noun-verb analysis. Right? You can look at the nouns in this description, and the nouns will tell us either information, data, or, in fact, classes or names of classes or objects. Okay? So what are the nouns in here? Node counter, well, we have that, right? Tree, that's a class. Pile, that's a class. Pile, get a tree, pile, subtree. Okay, what about subtree? Well, a subtree is a kind of a tree, so that's really means the same thing as tree. Split into two trees, resulting tree, discard the tree, node counter, pile, value of the counter. Standard output device, that's a noun. Now, the standard devices like this are mechanisms for getting information into or out of the system. As far as our analysis modeling is concerned, we're going to ignore those kinds of mechanisms. We assume that the display knows how to use the standard output device to print out the number. And we're not going to model mechanisms like devices, like input and output devices in our analysis model. Similarly, you wouldn't model buttons and menus and windows and stuff like that in your analysis model. The GUI and the user interface stuff is really part of design. So it looks like we found all the classes. Have we found all the objects, or excuse me, all the operations? Well, those will be verbs. Okay, so there's a verb, maintain. Well, that's sort of a noise word. Really, we don't usually treat that as an operation. Let's see what else. Get the original tree from outside the pile of tree. Yeah, that was an operation that we actually identified. Put, there's a verb. That was an operation on pile, right? As long as the pile is not empty. Okay, there's a verb. Right? Do the following. Well, that's a noise word. Do the following. Get a tree, right? That was an operation on tree or on piles. If the tree has subtrees, there's a verb. That was an operation. Split, that's an operation. Put, it's an operation. Discard, increment. Okay, these are all operations that we added to the classes. And display. So in this really simple example, the verbs and nouns pretty much correspond to the classes of objects and the operations. I will tell you, however, in a larger problem, you're going to have a lot more nouns, a lot more verbs than you really do have classes or operations. And this will break down, this little technique for identifying objects and attributes and operations will break down if you have a larger problem to solve. Something like once we were consulting with a team that was doing a big program. They had a statement of work that was 30 or 40 pages long. And they had gotten started earlier in the day. They were working in one of these big conference rooms that had whiteboards on all four walls of the conference room. And they were just going through this document and underlining, identifying nouns and verbs. And they were just listing these nouns and verbs on the whiteboards. And by the time we got there, sometime in the afternoon, they had filled up almost 3 whole whiteboards of the room with nouns and verbs. And they were only halfway through the document. It just gets unwieldy and very cumbersome as a technique using the nouns and verbs. So you have to use a little bit of intelligence. So this can help as a double check to see that in fact you do have all of the classes like we've done here. But it's a sort of a first cut. So it can help you in some cases to do the noun-verb analysis, and so that will be a technique for really small programs anyway. Okay, so those are our classes, and now when you execute the program, the controller will basically send messages to these objects to have it do their operations. So the controller would say to the tree, give me the initial tree, and the controller would have that tree, and of course then the controller would send a message to the pile to say, put this tree into the pile, right? And then go into the algorithm, okay, and the controller would say, to the pile, are you empty? And the pile would say, no, I'm not empty. Right? So then the controller would say to the pile, give me a tree, get a tree. So say you get a tree. And he would get the original tree, in this case. Right? And now the controller wouldn't know how to be able to deal with the tree because the tree is an object where the data inside the tree, the structure of the tree, is all encapsulated. So the controller would have to go over to the tree and send a message to that tree object, right? And the message would be has subtrees. So it sends this has subtrees message to that tree object that it just got off the pile. Now the tree, being a tree, it knows how to tell whether it has subtrees or not. It can actually look at the inside and see the encapsulated information. And in fact, sure, it has subtrees. So we would say to the controller, yes, I have subtrees. And then the controller says, okay, now what do I need to do? I need to split the tree into two trees. Okay? But the controller can't do that, but the tree can do it. So once again, the controller sends a message to the tree saying, split yourself. And the tree would split itself into two trees, return the two trees back to the controller. The controller would put both of those trees back on the pile. Okay? And that would be one iteration through the loop. Okay. So we go back up to the top of the loop. The controller would ask the pile, are you empty yet? And of course now the pile is getting deeper. It has two trees in it. And so the controller would say, well, give me a tree at random from the pile. So the controller would say to the pile, get. And then the pile would return a tree, one of the trees. The controller would send the message, has subtrees, to that tree. The tree would tell it whether or not it had any subtrees. And if it did, the controller would say to that tree, split yourself. If that tree didn't have any subtrees, then the controller would say to that tree, what? Discard yourself. And then also the controller would send a message to the counter, increment yourself. And so forth. And the controller would just invoke these operations by sending messages to the objects, either the object instance of the counter, object instance of the pile, or object instance of the tree, and using this as its algorithm. And eventually the pile will become empty, and then the controller will, the controller will say to the pile, are you empty? And the pile will say, yes, I am. And then the controller would send a message to the counter saying, display yourself. And everything will work all right, and the counter will display the correct value. So that's sort of the way it works.